All right, everyone. So let's get started with today's lecture. Today is the final day of the small language model workshop. Earlier, I had planned for only 3 days for this workshop, but today we will wrap it up with some very interesting production level projects, which I'm going to discuss with all of you. Now, to go into each of these projects, it will take a long time, maybe 3 hours each. So I'm going to condense today's lecture and I'm going to show you enough things so that you will be able to replicate both of the production level projects which I'm going to show you to do. So the first thing which we are going to learn today is we are going to learn how to replicate GPT-2 entirely from scratch. That's the first objective for today. And the second objective for today is that we are going to also build a small language model specifically in the biomedical domain. And I'll take you through both of these objectives. I'll also share the Google Colab code files with you after this lecture is done. For the second production level project, I'm still working through it, but I have taken it to a level where I'm getting decent results. I'll share that with all of you so that students and researchers who are interested, you can build upon this further. After these two projects are explained, I'll also explain to you how you can use these code files to build a small language model of your own choice and for your own application. If you have missed last lecture, you will be able to follow today because today we are not going to discuss any concepts really. In the previous 3 lectures, let me do a quick recap of what all we have seen so far. In the previous Let's see. Yeah, in the previous lectures, what we have seen so far is all of these 6 parts. So in day number 1, day number 2, and day number 3, we have seen assembling our data set, data pre-processing, assembling the model architecture, setting up the training pipeline, and then finally running inference. So today I'm not going to go through any of these concepts. Today our main job is to understand the production level applications. If you have missed one of the previous lectures, you will still be able to follow along in today's lecture, but certain portions. So for example, when I talk about transformer block, you will not understand what that means because that we covered in detail in the last lecture. So then you can go through the recordings. All the recordings have been uploaded on the dashboard. If you have registered for the course, you should see the lecture recordings on the dashboard. I upload them immediately after the lecture is over. So what we finished at the end of the last lecture is we actually built our own small language model fully from scratch. And we did this in the following steps. We imported the tiny stories dataset. After that, we tokenized the dataset. That was step number 2. After that, we created input output batches for the dataset. Then we defined the small language model architecture. After that, we defined the loss function. We defined the training configuration part 1 and part 2. Part 1 is essentially the hyperparameters and part 2 is the optimizer configuration. And then finally in step number 8, we pre-trained the entire small language model. So I showed you 20,000 epochs yesterday, and then we plotted the training loss and the validation loss. And many of you were able to also run inference along with me. So in the class yesterday, I ran inference on the small language model which we trained. And it was incredible to see that we produced coherent English responses. So just with a model with less than 100 million parameters, the model was able to learn the form and meaning of the English language. So we actually built, assembled, and inferred from a small language model entirely from scratch. The amazing thing of the architecture which we assembled is that at no point did we tell the model that this is the grammar rules which you have to learn, etc. It got that from the next token prediction task. All we did was take a huge amount of data. We split that data into training bin and the validation bin. And then we trained the model to achieve a good performance on the next token prediction task. That's the beauty of the next token prediction task, right? It seems very simple. You create input output pairs and then you just train to predict the next token. But as a byproduct, the model seems to learn about language itself. The main feature of this exercise was we showed that you really don't need a model with billions and trillions of parameter to understand language. You can do it with parameters of the order of 10 million to 100 million and still understand the structure and meaning of language. Today, we are going to look at two such small language models further. So the first task for us is to actually replicate GPT-2 entirely from scratch. So let me show you the pipeline of what we are going to do exactly today. Yes, so this is the whole pipeline uh, of replicating a GPT-2 from scratch, which we are going to see in today's class. The main GPT-2 paper which we are going to refer to is this one, which I'm sharing in the chat. So take a look at this paper, which mentions several aspects regarding GPT-2 architecture. What we are going to especially do is that we are going to use the small version of their architecture. So we are going to assemble an architecture which has 12 layers, which has an embedding size of 768 and overall which has around 117 million parameters. So yesterday, if you remember, we have taken a look at several of these hyperparameters. Can someone tell me what is the block size? We have seen this in yesterday's class also. What do I mean by block size over here? What is another word for block size? Context, right? Yes, this is what we have seen in yesterday's class also. Block size is essentially the context length or the context window. The vocabulary size which we are going to use is 50257. N layer, which are the number of layers. These are the number of transformer blocks. So we are going to use 12 transformer blocks, and N head is the number of attention heads. So we are going to use 12 attention heads in each transformer block, and the embedding dimension which we are going to use is 768. This is how we are going to construct the architecture. And what I've shown you in the previous class is we use this data set called the tiny stories data set, right? We use this data set, which has around 2 million rows. Today, we are going to go into production level data sets, which means data sets which are huge. So to build GPT-2 entirely from scratch, what we are going to do is that we are going to look at a data set which is called as the fine web EDU data set. And I've mentioned the link of this data set in the chat. This is the fine web EDU data set. It's essentially a refined collection of all the information which is present on the internet. And so the original data set for this is fine web. Fine web EDU is the subset of fine web dataset, which consists of educational content. So this dataset has around 1.3 trillion tokens, which is a huge dataset. Today, the dataset which we are going to use is we are going to use 10 billion tokens out of this data, which is pretty huge, right? So to compare the tiny stories dataset, if we take a look at the tiny stories dataset, it has around 2 million stories, right? It has 2 million stories, and if you consider each story to be about 50 words, let's say, and each word to be about 5 characters, that would be around, I would say, 500 million tokens. So the data set which we are assembling today is 10 billion tokens, which is around, I think, 10 to 20 times larger than the data set which we considered for in yesterday's training. Vocabulary size is not 10 million. Remember, vocabulary size is very different from the data set size. Vocabulary size is still 50257. This is the underlying data set which I'm talking about, the data set which we are going to train our model on. All these other parameters which I've mentioned, which we saw in yesterday's lecture, will stay the same, but the data set is going to be slightly more complex. There is a question for the small language model. Is there a specific reason behind these numbers? So I'm just using these numbers as reference for now, because overall, if you have a model with around 117 million parameters, it definitely classifies as an SLM. And GPT-2, the smallest size of GPT-2 can be called as an SLM. So we are just using the exact same parameters which this configuration had. So that overall the total number of parameters adds up to around 117 million, and that would classify as a small language model. So this is the data set which we are going to use. And finally, how will we know whether we are performing well or not? So there is an evaluation metric which is called as HELA swag. How many of you are aware of this metric or have heard of this metric before? Okay, so this is an evaluation metric and I've shared the link on the chat. What it consists of some questions, and then there are four completion options which have to be chosen from. So for example, the question can be something like this, or the incomplete sentence can be something like this. Then the man rides over the snow, covering the window of a car, and a woman wearing winter clothes smiles. Let's say this is an incomplete sentence, and there are four options which are given to the LLM, four possible endings. These are the four possible endings which are given to the LLM. And out of those, one of the endings is a correct option, which is more common sense. Humans can get these answers very easily, but for an LLM, it's actually very difficult to predict what the correct answer is based on common sense. So this is the HELA swag metric. So ultimately what we are going to do is that we are going to check our model performance based on how well it is doing on this metric. So if you give questions like this, is it able to get the correct answer out of these four options? Okay, so this is the metric which we are choosing. And there are some questions in the chat related to SLM and LLM architecture. Yes, they are the same. It's just about the assembly of the data set. The data set needs to be very specific, and the total model parameters need to be, let's say, constrained to less than or equal to, I would say, 100 to 200 million for it to be called as an SLM. There is no real definition of the exact number of parameters which quantifies as an SLM. Can you tell once how we calculate parameters of an SLM? So this we discussed extensively in the last lecture, Srish. So you can refer back to that lecture if you want that clarity once more. But today our approach is going to be very focused. We want to replicate GPT-2 from scratch today. And if you have any conceptual questions, you can refer to the three lectures which we have seen in the previous recordings. So this is the evaluation metric which we have. And if you take a look at this blog, so this is or rather a GitHub discussion, which was mentioned by Andre Karpathy around 1 year or 1.5 years back. And there he actually mentioned that he has tried to reproduce GPT-2 on the FineWeb dataset. So he trained this transformer on 10 billion tokens of FineWeb, which is exactly what we are going to do today. Take a look at the parameters which he has mentioned: 12 transformer blocks, 12 attention heads in each block, 768 as the embedding dimension. And then here is the results, right, which he has obtained. So the loss function should actually go down like this. And if you see the red dotted line, that's the OpenAI GPT-2 checkpoint loss. So ideally, if we start matching this checkpoint loss, it means that we are starting to replicate GPT-2 results very well. Take a look at this red dotted line. That's coming from the GPT-2 paper, which I just showed you over here. So if we have actually successfully managed to replicate GPT-2, our final loss, which goes on decreasing and converges, it should be as low as this. So that's the loss metric. And on the right hand side, you have evaluations on the HELA swag questions. And you will see that GPT-2 achieved an accuracy of around 0.295. And if our blue line eventually manages to achieve an accuracy of that, it means that we are even matching the performance metrics of GPT-2. So today we are also going to generate these two plots like this, the left hand side plot and the right hand side plot. And we are actually going to compare it with what GPT-2 obtained. In the class, I'm going to run less number of epochs, but later I'm going to show you how you can increase the number of epochs, and then you should exactly match these results. So you understood about the data set, what we are planning to do over here. You understood about the evaluation metric. There is one more thing which we are going to do today. As I mentioned in the last class, in this class, we are not just going to use one GPU. We are going to chain multiple GPUs together. So we are going to chain 8 H100 GPUs together for our pre-training. Because the data set is very large, if you just take one GPU, you will get out of memory errors. So one way to solve this is to chain a bunch of GPUs together. This is called as multi-GPU training. And this domain which we are learning about right now, it also comes under the domain of distributed computing. So the way this works is that, let's say we have 8 GPUs, right? And you have huge amounts of data. The data is split across these 8 GPUs. So GPU number 1 will have some data, GPU number 2 will have some data. Similarly, GPU number 8 will have certain data. When I say data, I mean input output pairs, which we saw in yesterday's class, right? So when a data is processed in one GPU, you remember what happens. You have the input. That input goes through the LLM architecture. Then we get the predicted tokens. Then we get the loss. And then we get the gradient of the loss. And after that, we do parameter updates. This is the whole workflow. So on one GPU, what happens is that you get the input data, it goes through the LLM, we get the loss, and we get the gradient of the loss in one GPU. Similarly, the second GPU, we get its own gradient, and the last eighth GPU will get gradient number 8. So we have 8 gradients coming from 8 different GPUs. And then what we do is that we average out these 8 gradients. So we take an average gradient across all of these 8, and then we update the model parameters. So since the data is split across multiple GPUs, every GPU computes the gradients in a parallel manner. So the speed is as if it's only happening on one GPU because every GPU is working parallelly at the moment. So the way this works is that one GPU, as has been mentioned in the chat also, one GPU will have certain set of batches. Other GPU will have another set of batches, etc. So let's look at one GPU right now. And if my input actually looks like this is one input X in on one GPU. Now, I hope all of you remember this shape. We have seen this before also. The number of rows here is the batch size of the input. So this is the X and Y tensor which we saw in the previous lecture. Just let me remind you. Yeah, this is that input tensor X which we have seen previously. I have just shown that same tensor over here with slightly increased parameters. So if you see, I'm now explaining to you how the data is split into batches. Imagine we have this huge amount of data, right? Let's say we have these 10 billion tokens which are there, which are converted into token IDs. On one GPU, what happens is that we have an input like this. And if the context size is 1024, can you compute how many tokens are there in one batch? So this is one batch on one GPU, which is called as a micro batch. So the micro batch size is equal to 64 and the context size is equal to 1024. So the number of tokens in one batch are 64 into 1024. And that is on one GPU. And similarly, we have 8 such GPUs, right? So in one batch, 64 into 1024 into 8. These are the number of tokens which are processed in one batch. So let me calculate this 64 into 1024 multiplied by 8. That's 52488. So this is equal to 52488. Now this becomes our batch size. This becomes our total batch size. So the total batch size which we have is 52488 tokens. Or 524,288, right? Yeah, 524,288 tokens, which are spread across each GPU. So one GPU will have 64 into 1024 tokens. And now, if you have 10 billion tokens, how many iterations will you need to do to cover the entire data set? If the data set, is 10 billion tokens, 10 billion iterations will you need to do to cover the entire data set? If the data set is 10 billion tokens, 10 billion iterations will you need to do to cover the entire data set? If the data set is 10 billion tokens, 10 billion iterations will you need to do to cover the entire data set? If the data set is 10 billion tokens, 10 billion iterations will you need to do to cover the entire data set? If the data set is 10 billion tokens, 10 billion iterations will you need to do to cover the entire data set? If the data set is 10 billion tokens, 10 billion iterations will you need to do to cover the entire data set? If the data set is 10 billion tokens, 10 billion iterations will you need to do to cover the entire data set? If the data set is 10 billion tokens, 10 billion iterations will you need to do to cover the entire data set? If the data set is 10 billion tokens, 10 billion iterations will you need to do to cover the entire data set? If the data set is 10 billion tokens, 10 bil And after you process one full batch, you take the gradient, right, and update the parameters. So how many total number of steps will you need to take? So the total number of steps which you need to take to go through the data once, to go through the entire data set once, that's equal to 10 billion divided by 524,288. 10 billion. So let's do this. That's around 19073 steps, right? That's around 19073 steps. And this is going to be one epoch. So to cover the entire data set, so let me repeat this once. Imagine our whole data has 10 billion tokens. We put them in a bag. Okay. Then what we do is that in one batch on one GPU, we have 64 into 1024 tokens. But across 8 GPUs, we have now 64 into 1024 into 8. So when one batch is fully processed, 524,288 tokens are fully processed. So in order to make sure that all the tokens in the dataset are processed, we have to do 19,073 update steps. So we have to do 19073 update steps. That is one epoch basically. Today, when we do the training procedure, I'm going to show you 2000 steps, which is not going through the full data, but it is manageable during the course of the class. And usually, as I mentioned yesterday, to train SLMs, you just need to do one or two epochs. So even if you do 19,000 steps, you will see that you actually get pretty good answers. In terms of the code, what we are going to do is that I'm sharing this link in the chat now. Um, we are now going to follow the code which has been mentioned on the screen I am showing you. And one thing which I want to mention to all of you is that when you scroll down the code, you'll see that, oh, it's so long and I don't understand any of this. What I want to bring to your attention is that the code which we have written in yesterday's Google Colab class is exactly the same code, because you will see the same architecture, right? We saw a block for causal attention. So here in the code, the architecture of the code which we saw yesterday and what we are seeing today remains exactly the same. So here also we had a causal attention block C, and here also we are having a causal attention block. Then you will have, this is the transformer block, and the entire feed forward step is the same as what we saw yesterday. You have the token embedding, you add it to the position embedding. This gives input embedding. The input embedding then goes through a series of transformer blocks which are chained together. Once we come out of the transformer block, there is an output head, right? And then after that, we have the logits matrix, which does the next token prediction. And then we have a loss function over here. So this entire forward pass is exactly the same as the forward method which we saw yesterday, which is this. Even the loss function calculation remains the same. So if you see the way the loss function is calculated over here, it's the cross entropy loss, which we actually spent a lot of time yesterday in understanding. The only difference in this code is that the data set which we are loading is different. And the second difference is that we are actually going to use distributed training. So we are going to divide the data set across 8 different GPUs. So wherever you see torch.distributed, that's actually doing that distributed training, right? And if you scroll down below, you should now be able to understand these metrics. This is exactly what we have discussed on the whiteboard right now. Take a look at the total batch size. It's 524,288, right? The micro batch size is 64 and the sequence length is 1024. This is the same thing which we saw, if you remember. The micro batch size, which is this, is equal to 64, and the context length, which they are also calling as the sequence length, is equal to 1024. So B into T, that's 64 into 1024, and DDP world size. So world size just means how many GPUs do you have. So in this case, we have 8 GPUs, right? So 64 into 1024 into 8, that will be equal to my batch size 524288. And if you scroll down below, you'll see the number of steps which we are taking here. The number of steps is 19073. That's the same calculation which we did over here. Uh, if you remember, this 19073 steps leads to one epoch. That's why it's mentioned here that number of steps is equal to 19073. That's essentially going to be equal to one epoch. And that's going to go through the entire data set once. So the difference between micro batch size and batch size is, can someone tell me now, based on whatever I've explained so far, what is the difference between micro batch size and total batch size? Yeah, so micro batch size is essentially restricted to one GPU, whereas total batch size is when we look at all the GPUs together, all the 8 GPUs together. Okay, I hope this is understandable to all of you right now. I think who asked the question? Dishant, I think, asked the question. Um, okay, so good. So next time when you look at this code, so this is that code which we are going to use in today's lecture. I'll show you how to use it, but don't be scared by this code, because the way this code is organized is that you have, the code starts with the architecture, the self-attention block, the feed forward neural network, the entire transformer block, which consists of the layer normalization, the attention mechanism, another layer normalization, a feed forward neural network, skip connections, etc. We have seen all of that in theory. Then comes the GPT architecture, where we have this forward method that goes through the whole GPT architecture, and we have the logits and the loss. You will see that this code has some other things also which we really don't need that much. The only thing which is needed is the evaluation on the HELA swag metric. And the other thing which you will notice is slightly different is the distributed training. So don't worry if you don't understand the distributed computing at this moment. I am planning to have other workshops on GPU distributed computing. At that time, I will explain all of this. For now, it is just important for you to understand where these numbers are coming from. 52488, this 64, 1024. What are these numbers? Because once you have these numbers in your mind, things will be easy for you to understand. And this maximum learning rate, minimum learning rate, warm up steps, these are the same parameters which we saw yesterday also. So what I want to point out here is that in the architecture itself, we are not really doing anything new. The architecture is similar. It's just that the data is different. So what is the difference in what we are doing today compared to yesterday? First is that the data set is different, as we saw. Second, we are chaining 8 H100 GPUs together and doing distributed computing. That's the only thing which is different. And third thing is that we are actually evaluating it on a metric which is called as HELA swag. Uh, was these number fine-tuning already? I don't think I fully understand the question. Are you asking whether we have done fine-tuning on this data set yet? Oh, like how do we fine-tune these numbers? How do we get these numbers? So the numbers are hyperparameter optimization. We have started with some numbers. So context size is fixed, but this micro batch size is something which is at our discretion. We can change it. The way Karpathy has done it here is that he has decided the total batch size once, which is 2 raised to 19, and then he broke it down further. Yeah, it was a grid search. So essentially, we have to start with some hyperparameters, and then we have to decide um, which ones are actually doing better. How do we decide the evaluation metric? So currently our goal is to replicate what GPT-2 did. So they had this HELA swag evaluation metric along with many other metrics. That's why we have chosen this to replicate. There is a question by Dishan that $25 which you mentioned. I'm going to come to that just in a moment. But yeah, the more number of training iterations you have, the more amount you will need on RunPod. Okay, good. So is it clear to everyone what we are trying to do in the first half of today's lecture, how we are trying to replicate GPT-2 from scratch? Now the practical tutorial is going to begin after this point. But I just want to make sure that the stage is set correctly, the context is set correctly for what we are going to do now. Because now I'm actually going to show you how you can assemble these 8 GPUs together and how you can actually start running the training process and start to replicate these results which you see over here. Okay, before actually doing that, all of you will need to download some files which I'm sharing right now. So I've created a folder called SLM workshop, and I'm just going to share this with all of you right now. So I've shared a Google Drive link on the chat. For now, what you can do is just download all of these locally, download these files locally. So just click on the download button. Here, if you see these three dots, download all of these locally. Okay, that's the first thing you have to do. And now let me show you how to actually start using RunPod. Right. So how many of you have used RunPod before? Or how many of you have used this interface which I'm showing on the screen before? Or is this your first time? First time? Okay. What about others? Good. Some of you might have used, for some of you, it's the first time, right? So let's follow the instructions step by step. First, what you have to do is you have to click on sign in. And if you have not already signed in to RunPod, you can simply do a sign in through Google. So it should be very quick and you should already be presented with a dashboard which looks something like this. Now, you won't be able to go ahead with this tutorial unless you have budget on your account. And I mentioned this yesterday also. We are going to chain 8 pretty powerful GPUs together. So at least you should have $25 on your account. How many of you have that budget right now? Can you mention in the chat? If you don't have that budget, it's totally fine. You can just follow along. Okay. Just try to see what is going on so that later when you load the account with this much credit, you can replicate this tutorial the way I am doing it. So the first thing which you have to do is click on pods. On the left hand side, click on pods here. So this is where we actually allocate our GPUs. Then what you have to do is that click on deploy. Here, click on deploy. And here is where we have to choose the different GPUs, right? You will see several GPUs, mostly all of them through NVIDIA. And some GPUs are expensive, some are cheap. So generally the GPUs which have more VRAM, which is one of the most important parameters, are more expensive. So for example, H200 has 141 gigabytes of VRAM. That's $3.79 per hour, but A40 is $0.4 per hour. L40 is even cheap. L40 is around $0.89 per hour. H100, so typically H100 and H200 are the most expensive. There is one more range on top of that, which is B100 and B200. That's sometimes not available. So right now I can see that it's not available. So you can even filter by VRAM over here. So as you increase the VRAM, you'll see that if I go to VRAM of 360, RunPod kind of recommends to me how many GPUs or which GPUs I will need. So today what we are going to do is that today we are going to go ahead with one of the H100 GPUs. So we are going to go ahead with this H100 PCLE GPU, and that costs around $2.39 per hour. And remember that we are going to chain 8 such GPUs together, right? So it will cost around $18 to $19 per hour. And you need that much amount. Although we are going to run it for 5 to 10 minutes only, and then you can shut it down if you want to reduce the cost. But RunPod does not allocate you these GPUs if you don't have that much credit. So I'm going to click on this right now, H100, and then you can give some name over here. You can give some pod name. So I'm going to say GPT-2 replica build SLM. So from scratch. So that's the pod name which I've given right now. And then what you can do is that click on this edit template over here. Click on the edit template and increase the storage volume to 200 gigabytes and 200 gigabytes because the data set which we have is pretty large. And then click on set overrides. One more thing you have to do is you have to click on change template. And just to be safe, I usually run these demonstrations on PyTorch 2.4.0. So click on PyTorch 2.4.0. How many of you have finished until here? Can you mention in the chat? Yes. Have you done until here? Good. If you have finished until here, the next step is just to click on, oh, actually, the most important thing we did not do, change this count to 8 GPUs. So here there is a GPU count, right? You have to increase it to 8 because we are chaining 8 GPUs together and then click on deploy on demand. So once you click on deploy on demand, the GPU instances um, will be allocated to you and it might take some time for the GPU instance to be allocated. For how many of you can you see the connect button over here? So for me, there is still some downloading and extracting taking place. But if for all of you, this sometimes does not happen. So if you already see this connect button over here, you can click on this button. For how many of you this button is clickable? So I should reframe my question. Um, it should ideally be clickable. I think I've ran multiple tests over here, so if it's not clickable. If the button is clickable for you, you can click on it right now. Yeah, yeah. Okay, good. So for many of you, if the button is clickable, ideally you should go ahead and click on it. Let me show you how to do it. So basically, which template is to be selected. So the template is PyTorch 2.4 as I displayed just before coming to this part. This is the template PyTorch 2.4. Yeah, so now I can see this connect over here, right? And you can see 8 GPUs have been allocated to me. The next step is click on the connect over here and you will see Jupyter Lab. Click on this. Once you click on the Jupyter Lab Jupyter Lab icon, ideally a Jupyter notebook should open for you. Like how it is happening for me on the screen right now. So how many of you are able to see this Jupyter notebook right now? Size of the data set is not 10 terabytes, Srish. The number of tokens are 10. The number of tokens are 10 billion. That's very different from the size, right? Okay. So now what you can do is click on this Python 3 and you can wait for me over here. How many of you have reached this stage? If you have reached until here, it's good. Can you just mention yes in the chat if you have reached here and see this blank screen, right? Like how I am doing over here. So Sita is saying, can you repeat the last two steps? So yeah, basically what you have to do, once the pod is activated for you, you have to just click on connect. You have to just click on connect and click on Jupyter Lab. That's it. So the last two steps are the easiest actually. Click on connect, click on Jupyter Labs, and then this particular notebook should be opened for you. Yeah, and the thing about this is that it's very pressurizing because you can see the money being drained here at the moment, right? The as so the more longer this lecture goes on, the more money will be drained. And that's the thing about GPUs, right? If you want to do production level LLMs, you cannot do it with just single GPUs. I'm assuming that many of you who are attending this workshop want to build industrial level applications, right? So you have to spend this much money to build these applications. Otherwise, it's just not possible with simple GPUs. Great. So next step, what we have to do is that these files which I asked all of you to download, the 4 files, you so before actually pasting these 4 files, there is one more file which I want all of you to download. And let me go ahead and paste that file in the drive folder. So now once you have seen that Jupyter notebook blank screen, that's good. But one more file which you have to download is this file. Along with downloading other files, this is also the file which you should download. So just click on download and download it on your local machine. Okay, good. And now that you have done that, let me show you the next steps. The next step is that file which you just downloaded, the nano gpt.ipynb, you have to paste it over here on the RunPod left hand side. So see, this file appears over here. You can just drag and drop from your file folder and place it over here on the left hand side. Okay, done that. Can you just mention yes if you have done this step? If you drag and drop this file and just click on this file. So when you click on this file, you will see a set of instructions which will appear. These are the set of instructions which we have to run. But please don't run this sequentially. I'll guide you through how to run this. The first thing which we have to do is that we have to clone this repository, because the main code files which we are going to use are from this repository itself, right? So what you have to do first is that there is this git clone command, right? You just have to run this command. So just run this right now. Yeah, you can see this is running. And then if you click on workspace again, you will see that a folder called build nano GPT should now appear on the left hand side for you. Is this folder appearing for all of you? This build nano GPT on the left hand side once you run the first command. Okay, now once that is done, just go to this folder. And what we have to do is these 3 files, right? We have to delete these 3 files and upload the files which I shared with you. So I've made some small changes in this file. So just go ahead and delete these 3 files: fineweb.py, hellaswag.py, traingpt2.py. Just delete those. And in that place, you can upload the files which I shared with you, the 4 files. So now I uploaded these 4 files again: fineweb.py, hellaswag.py, inference.py, and traingpt2.py. These are the 4 files which you must have downloaded from your Google Drive, which I shared earlier. How many of you have reached this stage where you see this much, where you see these files right now? Okay, good. What about others? Are you following along? Once you have these files, now you are actually ready to begin training the begin rest of the cells. So meanwhile, some people have asked for the drive folder access, right? Let me share that with you. Okay, now what we have to do as the next step is just go ahead and install these packages which are mentioned below. And it's fine if you get these errors. Your code will not stop because of these errors, just some different versions will be installed. So you'll get some errors like this, but it's fine. Now the next step is the crucial step, right? In this step, what we are doing is, uh, so in our organization's Hugging Face, if you see over here, um, actually, let me show you that data set. Yeah, so what we are right now doing is that This is our organization's Hugging Face. And what I have done is that I have already taken this FineWeb BDU dataset and I've converted it into token. I've converted it into token IDs so that it saves time for all of you. I've taken this dataset from Hugging Face and I've converted the entire dataset into token IDs. So if you go to this link, which I'm just sharing right now, this is that link which consists of yeah, so actually, if you go to this link, what we are doing right now is that we are going to download the token IDs essentially. So what I did is I took that whole 10 billion tokens, that whole data set, and I've tokenized it using the byte pair encoder. And the tokenized files I've saved over here. So in our collab, the first lecture which we did, this step was equivalent to this step, and it took a long time if you remember. This tokenization step took a very long time for us to create the token IDs itself. So here is the place where I've already created the token IDs so that for you it will be easier. Yeah, I think you are unable to open the link probably because it's not public or something, but it's fine. I think you should still be able to download these files from the code. Um, I will try to make this public actually. Let me see. Yeah, I've made it public right now. Can you check again? Yeah. So I've made it public right now. You can go ahead and check whether it's working. So this is the place where we'll download the tokenized files, right? So now let me jump back to my Google Colab again. Okay, so let me share my screen. Okay, so we are at this step right now. At this step, we are essentially downloading the tokenized files from my Hugging Face. So just run this. Are all of you seeing this downloading from what I'm seeing right now on the screen? Essentially, we are downloading the files from my Hugging Face repository on our Google Colab, or rather, I should say RunPod right now. We are not on Google Colab anymore. We are on the RunPod Jupyter interface. So if you are on H100, this will actually take place very fast. So believe me, if you actually there is a fineweb.py script here, which directly gets the data from the main repository and it tokenizes it. This takes a very long time to run. It takes around 40 to 45 minutes to run. And finally, it encodes the files like .npy files, which I've already done. So you don't need to run this file right now. So see, downloads and tokenizes the data and saves data shards to disk. This is what we are doing right now exactly. So now this is done, right, for all of us. So you should see that there is a folder called edu fineweb 10 billion, which appears on the left hand side. And if you double click on that folder, you should be able to see all these tokenized shards which appear over here. Okay, how many of you have reached this step? Can you mention yes in the chat if you have finished this downloading? Because if you have reached this step, now all of you are ready to go for the next step. Ultimately, this is that data which will be distributed across the 8 GPUs. That is correct. So we have allocated 8 GPUs right now. And now what we are going to do is that we are going to run this script called train GPT-2.py, and we are going to say that use 8 GPUs. So when immediately when you call this, what is going to happen is that this train GPT-2.py, which is there, this is going to be executed. And then the distributed training loop is going to launch where the data will be split across the 8 GPUs, and then the exact same procedure which we saw in yesterday's build SLM from scratch, that will happen, and you should ideally see the training steps on your screen. So run this right now. This is the last step for training. So I have run this right now, and sometimes what happens is, yeah, since I'm also running other tests on my RunPod, I get this memory error. But if you are not running other tests on your RunPod, you should ideally start seeing your training loop already happening like this. But for me, you can see that I've got an error that uh, I think there is a memory error here. It is because I also ran one test today morning. We should ideally run for all the steps, I agree, but then it will just cost more. So it depends on your budget, Dishant. If you are willing to go ahead for 19073 steps, you can go ahead. But the change which I have made in this script is that I have only ran it for 2000 steps, which you will see over here. Uh, yeah, here. I only ran it for 2000. Ideally, it should ran for 19073. You can run for all the steps. It will not cost more than $24, I believe. Okay, so once you start seeing the training process, it should appear something like this: step 0, step 1, step 2, step 3, etc. And you should start seeing the training loss decreasing as the number of steps actually increase. Can everyone actually share on the chat what are you seeing on the screen right now? Sometimes you also run into memory errors like I have right now over here. But if you have actually doing it on the RunPod for the first time, you should not get any error. So as Dayanand has mentioned in the chat, you have already, yeah, yeah. So if you are seeing this output which Dishant is mentioned, you are going in the correct direction. That's great. So once you start seeing this output, and actually, if all of you have $25 budget, you can change the steps to 19073, but you would not be able to see the output in this class then. It will take maybe more time. So Fazil has got this error, right? Which I also have got. So sometimes it happens that when RunPod allocate GPU, I don't know why it's stochastic in nature, but sometimes it works, sometimes it does not work. For example, today morning I ran this same code, exact same GPU configuration, and it worked. But right now I was getting this error. So as you are running the steps, you will see that I'll show you what the end result should look like. As you reach towards the end, you will see samples also being generated. So for example, if you are at step number 250, you will get validation loss of around 6.14. And you will see some sample being generated. Hello, I am a language model. That's the prompt. And the answer is a bit random at the moment. It's not really coherent English language. But as you go to step number, so if I scroll down below, and if I go to, let's say, step number 2000, things start happening really well because English starts to get a bit coherent. And remember, here we are training entirely from scratch on a 124 or 117 million parameter model. Hello, I'm a language model and it works really well. As I put it, the program is very good. So now English, at least coherent English sentences are being produced. And when you finish at the end of step 2000, the output starts looking something like this. Hello, I'm a language model, so let's talk about a new language, etc. And you can try this after this lecture is over, that if you run it for 20,000 steps, the final output is actually very good. The English sentences are extremely coherent. But right now, I just want to show you for 2000 steps so that the budget is not exceeded and we also finish it by the time the lecture is over. And once you finish the training, all you have to do in the last step is to run this inference.py file. So there is a file here called as there is a file here called as inference.py. What it will do is that it will actually try to mimic or try to plot your loss as compared with the GPT-2 loss and also plot the HELA swag evaluation score. So after running this stage, if you run this inference.py script, automatically an inference.png file should be loaded on the left hand side of your run pod. And if you open this file, you should see these results. The green line is the OpenAI checkpoint loss, and already we are only at 2000 steps, right? But we have already reached here. That's pretty awesome. And the HELA swag accuracy, we are only at 2000 steps, but we are slowly catching up. See, this orange line is what we have to beat. And I know it goes ahead after this point when you reach uh, 20,000 iterations. How do I know that? Because just yesterday I have actually ran this. Let me show you the results for 20,000 iterations. Yeah, so if you can keep it running, or if you're willing to spend more budget, you will actually get the exact same results as what I'm showing on the screen right now. So here, what you're seeing is that here there are 20, actually I ran only 18,000 steps, I believe. But can you check this right hand side plot? We have replicated GPT-2 fully from scratch, and we have even surpassed GPT-2's own accuracy. And we are slowly heading towards GPT-3 accuracy. We'll never reach GPT-3 because GPT-3's architecture size was pretty big. But this blue line is actually our training, which we are doing on the RunPod with the exact same code which I'm showing right now, but just for more number of steps. It's just that at 2000 steps, you are kind of this plot, this blue plot is increasing and it will slowly reach here, but it just takes more number of steps or more number of epochs to get here. Uh, so what Andre Karpathy got in his plot, which you see, so if you type Karpathy, yeah, this is that plot which many people actually try to replicate, this one. This is the exact same plot which we have replicated over here. And if you see the number of epochs which this person actually took to train is around 40,000. But you see here at 20,025, it already starts hitting that accuracy. But this person has ran it for 50,000 epochs. Of course, that will cost more. So for me, since this pod is not running right now, you see already $5 were consumed. I'm just going to stop this right now. And so remember, if you just stop without terminating, it will still continue to incur more cost because there is some volume being allocated. Right. So how many steps have all of you completed right now? Could you mention on the chat? Yeah, 50,000 steps would be approximately 2.5 epochs because 20,000 steps is approximately one epoch. 50,000 steps is approximately 2.5 epochs. Yeah, Peter, if you have got stuck at the errors, the only way to debug that is close your current instance and try running a new instance, maybe with A100 GPU or the different version of H100. Ideally, the exact same code should work for all of you. So I'm just going to wait for 5 more minutes till many of you actually finish running the different steps so that at least those of you who have reached the end, you should be able to see this inference plot during this class itself, and then you can paste your results on the chat. So meanwhile, let me take a quick break for 2 minutes. I'll come back. All of you who are actually running, you can also take a break for maybe 2 to 3 minutes. After the break, we'll see the results what people have obtained, and then we'll also have to see BioGPT. So I'll see you after 2 minutes, 2 to 3 minutes. Okay, so let's continue now. How many, can you tell me how many epochs you have finished for those of you who are running, especially? How many steps rather, not epochs, because to finish one epoch, it will take around 20,000 steps. So Dayanand, you have finished around 770 steps. Okay, good. So while you are running this, maybe I can go ahead and start explaining the BioGPT problem, and then we'll come back to this again and start seeing everyone's results once more. So the second part, um, yeah, in the second part of today's lecture, what we are going to do is that we are going to, I'm going to try to tell you how to actually build a small language model in a specific domain of interest. So let's say if you belong to the biomedical domain, or if you belong to the health domain, or if you belong to, let's say, aviation domain, or hospitality, mental health, whatever it is. And if you want to make a specific, if you want to make a small language model for your particular domain, I'm now going to tell you the workflow for achieving that. So the idea for this actually came to me when I read this paper called BioGPT. And let me show you, I'll also post the link of that paper. This is that paper. So what these authors actually did was, the authors are from Microsoft, by the way. They collected data from the biomedical domain. And where did they collect this data from? They collected the data from this website, PubMed. It essentially is a place of information with respect to all the papers, all articles with respect to biomedicine or biomedical research. So they took data predominantly from this website, they assembled that data, and then they build a small language model on top of that data. And the model which they built had around, I think, 130 or 140 million, around 300 million parameters, I think. So they did pre-training completely from scratch, and then they also did fine-tuning from scratch. So for fine-tuning, they would use different data sets. And all of this they put into an open source repository, which is called as the BioGPT repository now. This repository. I'll also share the link to this um, in the chat. The main issue with this repository, though, is that it's very difficult to understand really exactly what is done in this repository, and how to start with the data set, then how to do pre-training, etc. My main challenge with this was I wanted to show this in the same framework as we had learned the first project, the Tiny Stories project, and the GPT-2 framework, which we just saw right now. I did not want to change something completely. So my challenge was to um, bring this BioGPT repository into a Google code format, which follows a similar steps to what we have seen so far. So the steps will be something like this. We will be taking the data from the biomedical domain, and this data will be around 10 gigabytes of, it will take 10 gigabytes of space. We can take more also, but I took a subset of this data. Then we will tokenize this data, and then we'll create input output pairs, and we'll pre-train in an exactly same manner as what we did for Tiny Stories dataset. So once all of you start seeing enough applications run through the same code template, I think you will also be more confident to deploy your own SLM in your own domain. So we are going to do this right now. I'm just going to show you the entire Google Colab walkthrough for these. And then in that code, I have also actually done fine tuning. So I'll not explain the fine tuning part because that is not the purpose of this workshop, but that code is there for anyone who wants to. So I first did pre-training and did my evaluation. The results were not good. So I did fine tuning later. And the evaluation was performed on this dataset called Hallmarks of Cancer dataset. So this is a classification dataset where there are 12,000 pieces of text, and each piece is classified into one of 10 categories. Like one category is resisting cell death. There are 10 such categories. Actually, let me show you these categories for reference. Yeah, these are the 10 hallmarks. So the evaluation which I performed was, okay, you had this data set of 12,000 rows, and we know the correct answer to which category or to which classification that particular data set belongs to. And I wanted to use my pre-trained LLM to check whether this is good or not. And just pre-training such a small model does not lead to good answers. So I did a simple fine-tuning on this data set itself. And then the answer significantly improved a lot. I have still not matched exactly the same results which they have obtained. So for example, they have this table. I'm trying to replicate this table. My F1 score is currently at around 45 or 50. I'll slowly get there, I think, but this is a very good start for all of you to explore also. One more thing which we are going to do is that to do the tokenization, let's say we get the data, to do the tokenization, I'm not going to use the byte pair encoding, but I'm going to use their specific vocabulary which they have. So they have already mentioned the dictionary which they have, it's around 43,000 tokens. So this is how a vocabulary actually looks like for all of those who are curious about what a vocabulary actually looks like. This is a vocabulary, and you will see that there are around 43,000 tokens over here. So the vocabulary size here is 42380. And you also have merging rules. Uh, you also have merging rules. So merging rules essentially mention which tokens are merged. They also use byte pair encoding, I think, but I don't know which data set they use to train their byte pair encoding. So that's why we can directly use these merging rules on our data set itself. So we can use the vocabulary which they have and their merging rules to create token from the data set. Oh. Are you able to hear what I'm saying? Okay, the screen just froze for some time, so I don't know what is happening. Um, but yeah, basically what we are going to do here is that we are going to use their vocabulary and their merging rules essentially. So to again recap what we are doing, we are going to collect 10 gigabytes worth of data from this PubMed domain. Then we are going to tokenize this data set using their rules, using their vocabulary size and their byte pair encoding rules. And then we are going to follow exactly the same. So these same steps from step number 4, it's going to be the same. Actually, from step number three, 4, 5, 6, 7, and 8 are going to be the same. It's just that whenever you make your own SLM also, what will differ is step number 1 and step number 2. Step number 1 is where you will need to create or import your own data set, and step number 2 is where you will need to tokenize your data set. So these are the portions which might change. The rest of the architecture, you can use the same initial template and then later modify the hyperparameters. So I'm now going to share this BioGPT um, code file with all of you. Yeah, by the way, how many of you finished the 2000 epochs in the previous, in the GPT-2 replication code? Can you mention in the chat how many epochs you are finished? So Dayanand has mentioned that 1500 epochs. What about Dishant? You have finished 2000, but are you running for 20,000 or are you running only for 2000? Okay, so if you stopped, can you run the inference script? So basically the next two cells. And can you paste your inference plot on the chat which you have got? At least it will be a good indication that one or two people in our class right now have been able to run this live. For others, either it might be if you are not. Yeah, so see, this is the plot which Dishant has obtained, which is exactly the same as what I also obtained. And I think Dayanand will also obtain this plot very soon. So others who have not obtained um, the GPT-2 plot, which I just showed, which is basically this plot, these two plots, we should get not like this, we should get until iteration number 2000 will be at somewhere here. And then what you can do is after your class is over, you can just run it till 20,000, 30,000 epochs, and you would have completely replicated GPT-2 from scratch. Then you can upload your model to Hugging Face. You can even make a GitHub repository and add this project to your portfolio. You can add this project to your resume. But you won't be able to add it unless you run it for 18,000, 20,000 steps and replicate these results. But this is a very impactful project to actually perform. So I would encourage others also to finish this project after the class is done so that you also see these results. After training, how do we save our model? So if you see in the script of NanoGPT, not NanoGPT, if you see in the script of our tiny stories, we can actually save our model like this. We can save it in a .pt file where we save the model parameters here. And then every time we load the Google Colab, we just load this parameter file with which has all of our model parameters. That's it. So we don't need to run the pre-training again. But this part is very important. You can also very easily upload your model to Hugging Face. It does not take too much effort. If you just search about it after this class is over that I've pre-trained a model, how do I upload it to Hugging Face? You will just need to create an account on Hugging Face and then need to upload the model over there. Okay, so now in the last 15 minutes of the class, I will be going through the different steps which are involved in BioGPT. We won't be able to run it live because it takes around 45 to 50 minutes to run this. But let's first actually check the different steps, right? I've divided the script into two parts. Part one is the pre-training, and part two, if you scroll down, part two is the fine-tuning. Yeah, this is pre-training, and until step number 15, it's pre-training, and part two, it's fine-tuning. So we'll not look at fine-tuning right now. The results improve drastically if you use fine-tuning though. There is a question in the chat. So for training the vocab, which library should we use? Yeah, we usually use the tick tokenizer, which is a very popular library to do byte pair encoding. You can take a big data set, apply tick token, and get your merging rules. That's what the BioGPT people actually did, but we don't know what data set they used. Or what you can actually do is that you can also write your own byte pair encoder from scratch. We have done this in the Build GPT from Scratch course where uh, you can write your own compression script or BPE script from scratch. So now let me actually go through these 15 steps which are involved in the pre-training stage for BioGPT. And so it will be possible to do this project if you have an A100 GPU access. If you have a T4 GPU access, it will be very slow, but if you have A100 GPU, it will work. So the first step here is basically to load the data set from this repository, which I just showed you, this one over here. We are going to load the data set. And then what I'm going to do is that I'm going to collect the files from here until I reach a 10 gigabytes of size. So the reason I've restricted the size here to 10 gigabytes is because if it's more than 50, then you will not be able to do it on one A100 GPU. Then you would need multiple GPUs or an H100. The next step which I've done is that from each research paper which is there in this data set, we extract the title and the abstract and convert it into train.txt, valid.txt, and text.txt. Then comes our tokenization step. So we then apply byte pair encoding to our data set, where actually what we do is that we just take their we take their files, we take their we take their byte pair encoding merging code, and we take their vocabulary and we apply them to our data set. So this step which I've shown, what it does is that it actually takes our data set and creates token IDs. So that is step number 1.5, applying byte pair encoding to the data set. So then after this step, you will see that you have tokenized the data set, and then after 1.5, actually, it's the same procedure as what we did for the tiny stories. So just check it, just check the code here. I've actually copied the same code. If you see, step number 1.6 is create input output pairs here. And that's actually step number 3 over here, create input output batches or create input output pairs. So that's step number 1.6. Then I've defined the GPT architecture, BioGPT architecture. That's also the same as here. Define the SLM architecture. So after this point, I have not changed much. Define the configuration. The only thing which changes is the vocabulary size is 42380, whereas in GPT-2, we used a vocabulary size of 50257. Then you define the loss function. This is also the same. Training configuration is the same. The pre-training loop is also exactly the same. So I ran it actually for 120,000 epochs. And the training loss and the validation loss, which are decreasing pretty smoothly until all of these. So I could see from here that my model trained very well on the underlying data. And then I evaluated this on the hallmark of cancer data set. So here what I simply did is that I had these 10 hallmarks, right? And I knew for which data, which hallmark is the correct one. So I just got my LLM answers or my trained SLM answers, and I compared with the actual data. And I computed the F1 score, precision score, recall score. It's very bad. It's around overall 0.05 or 0.1, etc. And that's not surprising because we did not fine tune on a classification task. So if you are building, let's say, a chatbot, a small language model chatbot, which is a classification chatbot in the mental health space, just pre-training will not be enough. You will need to fine tune it on a specific data set for classification also. Because if you just do pre-training, the model sometimes answers in full sentences. It does not know that it has to just select between these classes. To help you with fine tuning, I have also attached a fine tuning code over here. And although I won't go through it right now in detail, I've extensively commented it. So you'll be able to understand what is happening in every single step over here. But I'll just show you the result towards the end of the fine tuning. After we actually do the fine tuning, all the values tremendously increase. So take a look at these values. I've got recall values of around 0.9, 0.8, and the average F1 score is around 0.5. This is a 5 times improvement as compared to what we obtained from just pre-training. And I fine-tuned on this hallmarks of cancer dataset itself. So naturally, we expect to get better answers, but it's a huge jump in terms of improvement. I'm still working on this code and I'm trying to eventually match their results which they got. The F1 score which they have, the recall score which they have, the precision which they have, etc. Actually, I've even surpassed the F1 score of GPT-2 medium, which had an average F1 score of 24.68. But this was for a different data set. For this data set, even GPT-2 medium had an F1 score of 80. I am still at around 50 or 60. But I think with taking a more detailed look at the code, I will eventually get there. So now let's say if you want to build a small language model for any domain of your choice, all you have to do is first collect a specific data set. collect a specific data set and just take it till the tokenization stage. Collect the data, tokenize the data, and then after this point, everything can be followed through this code template, which we have seen in the tiny stories SLM code. And if your data set is large, then you can chain multiple GPUs as we saw in the RunPod example. If, for example, an A100 is not suiting your requirements, no need to stick to Google Colab. You can use RunPod where you can actually select GPUs based on their VRAM. So it's much more customizable that way. Uh, there is a question regarding new models operating directly on bytes. Yeah, there are some models which completely bypass tokenization, but I have not really tested those yet. How to prepare data for a specific domain. So let me, when you go through this code in detail, you'll see what is done, because once you download the data from this folder, the data is downloaded in some weird formats like .xml, .gz, right? The data is downloaded in this format .xml, .gz, and then you have to convert it into txt format. Here also I have the code to convert the data from .gz, a compressed file, to a txt format. Once you have the data converted in txt format, you can easily do the tokenization after that point. Okay, good. We can see that Dayanand has also obtained his results on the chat, where he has he has replicated GPT-2 for 2000 epochs. That's great. Now, if you continue this for 20,000, you'll be able to match the GPT-2 results exactly. When you say collect the data, in what form should we connect? What form should we collect? So there are some tokenizers which are multimodal tokenizers also. Currently, all of the examples which I've shown you, the three examples, the tiny stories example, the GPT-2 example, and the BioGPT example, all of this had textual data predominantly. So if you're dealing with data which consists of numbers, you will need to use modern tokenizers for that. Maybe try to use a GPT-4 tokenizer, let's say, which is provided through tick token. If you are using multimodal data, then there are some different ways of tokenization. For example, image needs to be tokenized in a different manner. There are some open source tokenizers for dealing with images and tables as well. But even though you have multimodal data, once you finish the tokenization step, even with multimodal data, the rest of the steps remains the same. You just have to figure out which tokenizer to use. So for example, if you search multimodal tokenizers, I am sure there would be a list of multimodal. Yeah, see, already there are tokenizers like Lava HF, for example. This is a multimodal tokenizer. Maybe you can get started with this if you are dealing with data which has images, etc. So start with multimodal tokenizers like this, convert your data set into tokens, get input output pairs, and then proceed in an exact same manner as we saw for the SLM from scratch for the tiny stories. Fazil has also got answers. Okay, great. So I think 3 students from our class completely replicated GPT-2 until 2000 epochs. I'm sure others will also do it after the class is over. BioGPT link, right? Yeah, so BioGPT link I already shared on the chat. Let me share it once more. How do we select GPUs for our use case? That's a good question. So let me give you a quick walkthrough regarding that. So if you are on RunPod, right? If your problem statement does not have too much data, or if your context size is not very high, start with small GPUs. Start with A40 maybe, or start with L40, whose pricing is less than $1 per hour, 0.4 or $0.8 per hour. Their VRAM is also pretty low. But if you have huge amounts of data, let's say, for example, the FineWeb EDU dataset, which we had 10 billion tokens, right? For that, you need GPUs which have a higher VRAM. So for that, either go with A100, which has 80 to 100 gigabytes of VRAM, or H100, which has around 140 gigabytes of VRAM. B200 is the highest, around 180. You won't need that probably. So start very slow. So let's say you go with A100 and you figure out that even one GPU is taking a long time. So if one GPU is taking 8 hours, it might make sense to chain 8 GPUs together because it might cost the same to you eventually, right? One GPU might take 8 hours, so it will bill you per hour. If you chain 8 GPUs, it might take 1 hour, but ultimately the costing would be similar and your time would be saved. So sometimes even going with one GPU and running for multiple hours might not be an optimized solution. But Google Colab actually does not provide you the option of choosing from different GPUs at all. That way, RunPod, there are some other options also. For example, Lambda Labs is one very nice GPU provider which through which you can provision GPUs. One more is TensorDoc, which also you can use to provision GPUs. No, we have to handle parallelization ourselves. RunPod will not take care of that. We have to write the code for parallelization ourselves. So if you see in this code, we have written here that number of GPUs I have is equal to 8, etc. And we have written some code for how to split the computations across the GPUs. Yeah, so this step, for example, says that once you get the gradients from all GPUs, you average them, etc. We have to specify that logic, but it's extremely important. It comes under the domain of parallel computing and GPU programming. Yeah, AWS, GCP, they also provide GPU instances. Now, the disadvantage of RunPod is that, so I have all these pods running, right? If I pause this right now and if I come tomorrow, there is no guarantee that this pod will be allocated to me. Then I will have to basically start a new instance. So what big companies do for this is that if they select a GPU, they go with this, they actually reserve a GPU, and that's very expensive. If you want to reserve a GPU for 3 months so that it's always allocated to your organization, you have to pay $8,000. If you have to reserve it for 1 year, you have to pay $30,000, etc. Yeah, so that's the trade-off between on-demand GPUs versus reserving GPUs, really. So now we have come to the end of this lecture, and let me quickly summarize what all we have seen through this SLM bootcamp so far. So we have had 4 lectures until now, and I think the total duration of this bootcamp is now around 7 hours. Earlier, I planned to do it only for 5 hours. But for those of you who have attended all of these lectures, it's amazing because now you would have learned the entire pipeline, right? In the initial lectures, we learned about all of these 6 parts: data set, data pre-processing, which involves tokenization, which involves input output pairs. Then we assembled the model architecture. Then we had the training pipeline. Then we pre-trained the SLM, and finally we ran inference. These are the steps which we saw. And then we actually saw 3 examples. We saw running an end-to-end SLM on a tiny stories dataset. After that, we replicated the results of GPT-2 for 2000 epochs, and the results will exactly match what you're seeing on the screen right now for 20, if you run it for 20,000 epochs. And the third thing is we started replicating or started developing a small language model for a specific domain, which is biomedical domain. One thing which I want to mention is that for all the 3 applications which I've shown you, I've tried to maintain a very common code base so that you don't get confused. So when you want to make your own SLM, you always go ahead with this code base. In fact, for people who are enrolled in the pro plan, the capstone project is going to be build your own small language model in your own domain. I'm going to provide instructions for that capstone project on our Discord. And for that, all of these Google Colab notebooks, which I'm sharing with you, are going to be very important to all of you. One more thing to mention is that the reason this bootcamp ran for a long time is because I went a lot into theory, which I believe is extremely important. Because if you go through the code, these portions of the code, right? These portions of the code, they show the entire transformer block, the input, the processor, and the output. But that takes around 2 to 3 hours to completely understand. And even more if you really want to spend time yourself writing down the matrix multiplication. So anytime you are confused, just remember this entire journey of a token as it goes through the architecture, right? Token embedding, position embedding, input embedding. Then the transformer block itself has multiple layers. Then within this, there is this multi-head attention layer, which is the brain and where all the magic happens. We also then saw how the attention mechanism actually works with the trainable query matrix, the key and the value matrix. Yeah, and then finally we saw how to get the context vector matrix from the embeddings really. This thing which I'm highlighting right now is where all the magic really happens in SLMs, right? This is where the context is understood and the language model knows really what to do. So a good LLM engineer or a good ML engineer, if you're in industry and if you want to transition, you not only need to have projects, but you need to have foundational knowledge. And then you need to start working on research projects that will truly distinguish you from others. Because not very many people will have on their resume that I built a BioGPT from scratch and I replicated their results. Because it's a very difficult thing to do. RAG, on the other hand, there are people now who have tutorials who explain a RAG project in 5 minutes. So you can easily watch that tutorial, put it on your resume, right? But no, it's very hard to actually replicate a research paper end to end. And if you have that on your profile, that is what will truly distinguish you from your peers. And that is truly hard work. And attending this workshop, I believe, is the first step for all of this. I have shared all the notes and the Discord with people in the pro plan. So you should all have access to this. So thanks everyone. Thanks for attending all of the lectures in the small language model workshop. I will upload all of these lectures, videos and the notes on the dashboard immediately after this lecture. And now it is my hope that you start building your own SLMs in your own domain. Thanks everyone, and I look forward to seeing you in other such sessions. See you. Bye.